Welcome. In this video about abstract data structures, we're going to be focusing on trees. As you can see, I've written down a definition here. A tree is a connected, undirected graph with no cycles. Now, if you're not sure about graphs, we'll cover that in another video. So, if a tree is a connected, undirected graph with no cycles, we can class the following as trees. This is a tree. This could be a tree. This could be a tree. This could be a tree. But this could not be a tree. Because we have a cycle. So the cycle is the idea of going back to one of the nodes. So I've said a few words there that might be unfamiliar to you, such as nodes. So first of all, we'll just label one of these trees. So if I just draw one of the trees a little bit bigger down here. So let's draw this tree here. And then we'll start talking about. And I'm just going to put some values into what we call a node. A node, in this case of the diagram that I have drawn, is each one of these circles here. And now I'm going to label it. So the circles, as I've said, we call these nodes. Another term that you might have heard of is a vertex. You could obviously refer to many of these nodes as vertices. The lines that connect the nodes are called edges. Now, in this particular example, I could actually call this node here a root node. And therefore, if I've identified a particular node that I want to class as my root node, I can refer to this whole tree as a rooted tree. So a rooted tree is a tree that has a root node. If I just draw one of the other examples from earlier, for example, this one, but I don't think I drew this one, but this could be classed as a tree as well. But I haven't identified a root node to this tree. Therefore, we wouldn't classify this as a rooted tree. Just coming back to the labels, a rooted tree is said to have parent and child nodes. So in this case here, when I look at the node with the value of b, we could say that this is the child node of the root node a. But we could also say that this child node b is actually a parent node to the child node d. So b, in the context of talking about b to the root node a, it is classed as a child. But in the context of talking about the node b with the node d, we'd say that it could be a parent. So depending on the context in which you're talking about the root node b, it is either a child or a parent. These nodes here, which you would say probably at the bottom of the tree, we call these the leaf nodes. Now you are a leaf node if you have no children attached to you. So this here could also be classed as a parent and a child, because it is C, the node with the value C in it is the child of the node A. But it is also the parent node of the child node F. And as you can say, the node with the value F in it is a leaf node. Something else to be aware of is that we can talk about levels, or we can talk about, in fact, we'll talk about levels of a tree. So we have a level here, which is the root node. This is level 0. We have a level here where the B and C nodes are, and this is level 1. And we have a level here where the nodes of values D, E, and F are, and this is level 2. So when we're talking about levels, we talk about ascending order from the root node. So 0, 1 to 2, where the base is the leaf nodes. But we could also talk about height, which is very similar to levels. But in terms of height, we talk about height being starting from the leaf nodes. So this is 0. This is height 1. And this is height 2. So we could say that the height of this tree that we're looking at here has a height of 2. The height actually comes into play when we start talking about the big O in terms of inserting values into a tree, searching values in a tree, deleting them, or simply accessing them. So the height can become an important factor with regards to trees when we talk about those things. Now, we do actually have different types of trees. So if I go back to drawing a couple of these trees here. So this is a valid tree. Yep. This is also a valid tree. But the thing that's different about each of these trees is that this one is classed as a binary tree. A binary tree is a tree where each node can either have 0, 1, or a maximum of 2 child nodes. And as you can see here, this node has 2 child nodes. This node has 2 child nodes. This node has 1 child node. We could even do another node down here and another node down here, but each of these nodes cannot have more than 2 child nodes. Whereas on the left-hand tree here, it's almost valid as a binary tree in the first 2 levels, but when we get down to this second level here, you can see that there are 3 child nodes attached to this parent node. And so this cannot be classed as a binary tree. We would just simply refer to this as a tree. You can see that I could identify this node here as my root node. So we could say that this is a rooted tree. But we tend to talk about rooted trees in the context of binary trees, and you'll see why we talk about those shortly, because they have many uses. Not that trees in general do not have uses. In fact, you might have seen a similar structure to this tree when you're talking about things like file management. So if I just draw this ever so slightly differently and imagine that this is a folder where you save your files, you might then have a folder inside of here, which has a folder inside of itself here, but it also might have another folder here, and it might have another folder here. So our file management system is actually using a tree data structure to organize itself. There are other examples as well, such as the layout of web pages when you build a web schema. So if I was building a website, I might illustrate that through a web schema where I'm talking about this being my home page. These are all the subsequent pages in my website. And again, these subsequent pages might not just be limited to 2 subpages. There might be more. And so again, this is a tree data structure. We wouldn't class either of these as binary trees, but we could certainly classify them as trees. There are other types of trees as well. You might have heard of an ABL tree or a B tree, but we're going to particularly focus here on binary trees. So again, a binary tree is a tree where each node can have a maximum of 2 child nodes. Examples of where binary trees might be used in computer science are you could have decision trees for machine learning. You will see when we talk about reverse Polish notation, we can use a binary tree for binary expressions. And we have another sort of tree that extends a binary tree, which we call a binary search tree. So it looks exactly the same as a binary tree. But if I was to draw, for example, a duplicate of this binary search tree on the left here, if I were to put values inside these nodes in a binary search tree, the idea of that is that if I wanted to insert the values 22, 10, 25, 9, I would take the first value and put that in the root node here. I would look at the 10, and the idea of a binary search tree is that any values that you insert into it are put into the tree in order. So if the value 10 wants to be put into this tree, it is less than the value of the root node, which is 22, so I put it to the left of that. If I wanted to put the number 25 into this binary search tree, that is greater than the number 22, so I would put that to the right of it here. If I wanted to put the number 9 into this binary search tree, well, the number 9 is less than 22, so I go to the left. The number 9 is less than the number 10, so I go to the left, and I could place that number here. And that would simply continue. So again, if we just try and insert the number 32, I'd say, well, 32 is greater than 22, go to the right. It's greater than 25, so go to the right, and I could populate the number 32 here. If I continue with a few of these numbers, so for example, 12, it would be go to the left. It's greater than 10, so go to the right. I could populate that here. And if, for example, if I had the number 24, well, it's greater than 22, go to the right. Less than 25, go to the left. And I could put 24 in here. And again, just to say that I'd constructed this tree prior to actually entering these values. So if all of a sudden I had another number, such as 63, I could check it against the root, go to the right because it's greater, check it against this part of the subtree. It's greater than 25, go to the right. It's greater than 32, so construct another node to the right because it's greater than 32 and place that value inside this node 63 here. Now, why is that different to a binary tree? Well, in general, a binary tree without the word search there, we could just put these values wherever we want without any particular order. So we could put them 25, we could put 9, 32, we could put 12, we could put 24, and then we could construct another node, and we could, if we wanted to, just put that other node here, put 63 there. So there's actually no order in which these values have been placed into the tree. Now, as you can probably see, one of the benefits of a binary search tree is that if I wanted to search this tree, the big O of searching this tree and accessing a value in this tree, or inserting a value into this tree, or deleting a value from this tree is actually log n. Because as I place the values into the tree, I was placing them in a particular order. You could also say of this tree that it has a big O of h, where h is the height, as we've already discussed, but there are some limitations to that. And so we would always be better off saying O of log n. If I just give you an example, this would be a valid binary search tree. but so would this. Okay, so both of these are valid binary search trees. Depending on how I enter the values into the tree. But if I was talking about the height of each of these trees, I could say, well, the height of this tree on the right is 0, 1, 2. And the height of this tree on the left is 0, 1, 2, 3, 4, 5, 6. So if I was talking about the big O of H, where H is the height of the tree, the big O of H with this tree here is the same as saying the big O of N. Whereas the big O of H for this tree here would be the same as saying the big O of log N. Okay, so we're better off always saying that the actual way to express the big O complexity for binary search trees, for access, search, insert, and delete, we would tend to say it's the big O of log N. To conclude, we'll just revisit something that was said earlier in terms of what are the uses of, for example, rooted trees. And as I said before, rooted trees can be used for helping us evaluate binary expressions, which you would talk about and learn about when you study reverse Polish notation. We can use them, rooted trees, as binary search trees, so we can use them for searching purposes. You might have also, as I said earlier, heard that you can use rooted trees for machine learning when constructing decision trees. Machine learning. Oops. So using a rooted tree for binary expressions, this would simplify for the computer the process of the processing of the expression. That's where we could use them. We might use rooted trees to construct a binary search tree so that we could speed up searching. And with regards to decision trees, this is just another use in terms of implementing machine learning.